Hi all, I welcome you all to the next lecture here, Professor Ravi Kumar, School of Mechanical Engineering, Shastra Deemtu University. So, agenda for today's discussion is to derive the different thermodynamic relations, right, using the concept of partial differential equation. Prior to this lecture, we have covered the third unit, and third unit basically was fully dedicated to the properties of pure substance and introduction about real and ideal gases also were given to you, and we have seen the in-depth concepts of ideal and real gas, one what way real gases are different than the ideal gases. So today we will derive various thermodynamic relations, right? Relations for TdS equations, relations for Cp and Cv, and then to express the Cp and Cv in terms of uh, bulk modulus, right, or coefficient of isothermal expansion. So these all things will be derived with the help of partial differential equations. So prerequisite for the today's lecture, you must have thorough knowledge of partial differential equations, how to deal with the exact differential and all. So I would suggest each and everyone should have the pen and paper with you so that you can follow the steps of parallel to me. All right, so let's start our discussion for today. So first is we'll see some fundamentals of partial differential equation. So how to derive the partial differential equation for a any function. So let there are three variables x, y, and z, and their functional relationship may be expressed in the following form. So function x, y, z is equal to 0. This is my equation number 1 fundamental, where x, y, z, these are the three variables and they are dependent on each other. So we can say x is also a function of y and z because x depends on y and z. Similarly, y also depends on x and z. So we can write these three equations out of this function. So we can say x is equal to x, y, z, equation number 2. Similarly, we can write y is equal to y, function of x and z, equation number 3. And z is a function of x and y. So we got these three equations right from a single functional equation, that is three variables, they are dependent on each other. So now as I said that x depends on y and z, if I am going to write the total derivative of x, that means I want to write dx, that means I have to use the partial derivative of x with respect to y, keeping one variable constant, then second differential of second derivative by keeping the first variable as constant. So I can write basically three equations out of these three equations, second, third, and fourth. Using these equations I can write three different partial differential equations. So let's start with the first. So let x is a function of two independent variables y and z, right? Y and z independent variable. Based on that, x basically depends on them. So we can write the differential equation for dependent variable x. Dx is equal to dou x y dou y, keeping z as constant dy, plus dou x y dou z, keeping y as constant dz. So if you look at, if we cancel out this and this, we'll get basically dx at the end. So the infinitesimal change in x quantity, it can be given as dou x y dou y z dy, and dou x y dou z y dz, right? So this equation in this dx is basically an exact differential. This is an exact differential, right? So let's suppose the first parameter, this parameter dou x y dou y z, I am representing by m, and this is another n. So I can write dx is equal to m dy en dz, right? So let's suppose this is dou x y dou y is z is em, and dou x y dou z y is en. So I can write dx is equal to m dy and dz. Now if I differentiate this m with respect to z, keeping y constant, and differentiating n with respect to y, keeping z constant, if these two variables are the same, then I can say the given equation is an exact differential. Or if it is not equal, in that case it is not an exact differential. So the partial differential of m and with respect to z and y, if we write, if we are differentiating m with respect to z, keeping y constant, so dou m by dou z can be written as the same equation, right? We have differentiated with respect to z, so we can write dou square x y dou y dou z. Similarly, dou n by dou y, we are getting dou square x y dou z y dou z into dou y. If you look at these two terms, both are equal, right? So we can say dou m by dou z is equal to dou n by dou y. If this condition satisfies, right, in that case we can say the given equation that we have written here is an exact differential. If it is not equal, right, in that case this will not be an exact differential. And from the definition of a property of system, we already proved that, right, all the properties of system form the exact differential. If it is not exact differential, they cannot be considered as the properties of system, right? So this is the necessary condition to be satisfied when we say the given variable is a property of system, when dou m by dou z is equal to dou n by dou y. Keep in mind, this is the first equation which you have written is m dy en dz. Immediately after that you have to find out dou m by dou z, that is em with respect to second variable, and n dou y, right? If these are exactly equal, then you can proceed further and you can say the given variable or the given quantity is a property of system, right? Then similarly for second equation, third equation, y is equal to y x z, z is equal to z x y. These three equations basically we have written. So first you have written one equation. Similar way you can write for second as dy is equal to dou y by dou x z dx and dou y by dou z x dz. Similarly, third equation is dz can be written as dou z by dou x keeping y constant and dx plus dou z by dou y keeping x constant dy. So you have now having three equations, right? And all these three equations should satisfy such kind of form of partial differential. Like if you want to write for this, right, this in this case, right, when dy is equal to dx and dz, then you have to write dou m. If you are saying this is m and this is n, you have to say that dou m by dou z is equal to dou n by dou x, right? In this case you have to say dou m by dou y is equal to dou n by dou x, right? If that is going to satisfy, you will say these variables are also the properties of system. So now look at this equation. This equation is having dx and dy. Already you know dy, right? Dy is here. So or you can either you could put the value of dy here, or you can take the dz value here and you can substitute here. So what I am doing now, I am substituting the value of dz from this equation, this complete equation here, right? I am adding these two equations basically. So if I do so, I can write this equation, right? So dy is equal to dou y by dou x dz x and dou y by dou z x, and this is the value of dz which I kept here. Now you multiply inside. If you multiply inside this term, right, this term here, right, you multiply inside and rearrange the terms, take this dx, these two terms with this dx and remaining terms as a dy. If you rearrange, right, you can write in this way. So first term of dx is this, second term of dx is these two, these are here dx plus this and this term will form dy. So I have written this, right? So further if you solve this, right, if you solve this further, you can write in this way, because this, you look at this dz and dz and dy will cancel out because both are the function. In both the cases x is a constant, right? So you can simply cancel out. So this is going to be cancelled out. Here I am getting only dy. So term became this dx plus dy, take this dy this side, so I can write this complete equation equal to 0, right? Because anyway this is going to be equal to 0, so I can write this complete equation equal to 0. Now take this equation this side, right? So I can write dou y by dou z x, dou z by dou x y is equal to minus sign and this term. Then you divide this term from this side here, right? So I can write dou x by dou y dz multiply by dou y by dou z x and dou z by dou x y is equal to minus 1. So that's the thing happened, right? First I have taken this side, then I have divided this complete term by this term, and I rearrange the terms. I got this equation, right? Dou x y dou y is and dou x y dou z by dou x y, and then finally this term, right, dou y by dou z x is equal to minus 1. So this is the fundamental equation which I got by adding these two equations. So let's suppose if we say that x, y, z are the variables, they are now replaced by pressure, volume, and temperature, because those means fundamental properties of a system is pressure, volume, and temperature. Let's suppose x is pressure, y is volume, and z is temperature. I can write the similar sort of equation for all these three equations in this way, right? So look at each and every term, right, present in this. All right. So if you look at each and every term, so we can say from here, x I said is a pressure. So look at here x. So x is represented by pressure, y is represented by the volume, z is my temperature. So by using this analogy, right, this equation, I can write a single equation for all the properties in this way: dou p by dou v at t, and dou t by dou p v is into dou v by dou t p is equal to -1. So this is basically the fundamental equation of all the properties. So all the properties will be related by these partial derivatives, right, is equal to -1. Next topic is Maxwell equation. So Maxwell given basically four important equation by which we can relate all the eight properties of the system. What are the eight properties of system? Pressure, volume, temperature, enthalpy, internal energy, entropy. Right, then Helmholtz function, Gibbs function. Right, these all different properties of system can be related by using the Maxwell equation. So a pure substance existing in a single phase has only two independent variables that we know. So if we want to fix the state of a pure substance, we need two independent variables, right? That is known as two property rule. And of the eight quantities, right, these are the different properties, right, of systems of pressure, volume, temperature, then entropy, internal energy, enthalpy, Helmholtz function, and Gibbs function. These can be related by using the Maxwell equation, and they can be expressed as a function of any other two properties, right? So for a pure substance undergoing infinitesimal reversible process, we can write du is equal to TdS minus PdV. Basically this is nothing but your first law of thermodynamics. So as per the first law of thermodynamics, we can say Q is equal to du plus PdV. I have taken PdV this side, and this is basically Q for reversible process T into ds. So du is equal to TdS minus PdV. This is the first equation applied for a non-flow processes. And then for flow processes, we can say instead of du, I can write dH is equal to du plus PdV plus VdV. Alright, but if you look at this term, right, du plus PdV is nothing but TdS. From this equation, I can say du plus PdV is nothing but TdS. So I have put it here TdS plus PdV. So this is the first TdS equation. This is the second TdS equation. This is applicable for non-flow processes. This is applicable for flow processes, right? Then second means the third equation is basically this is nothing but Helmholtz function, and Helmholtz function is defined for non-flow processes, right? So du minus TdS minus SDT, right? SDT. So now look at this equation, right? Du minus TdS. Look at this equation. Du minus TdS is nothing but this is minus PdV. So in place of this, I can write this minus PdV minus SDT. This is the third equation. Now next one is Gibbs function. This is applicable for open system G. So this is H minus TdS, right? So I can say this is change in that one. I can say dg is equal to dH minus TdS minus SDT, right? So instead of TdS where T and S both are variables, right, you have to differentiate independently. First is TdS, then SDT. So dH minus TdS, right, this equation we can use this equation. So look at here, dH minus TdS is equal to VdP. So we can combine with this, right, and we can write the equation d is equal to VdP minus SDT, right? Why basically we have expressed every equation in terms of PdV? Because P, V, T are the fundamental properties of system, and change in entropy as well also can be considered as a fundamental properties of system. So we have expressed U, H, F, and G in terms of two other independent properties, right? So now we use the concept of partial differential equation that been discussed earlier. So any change can be written as mdx and dy. So you just focus on this. This is nothing but du, change in any one variable is equal to m. This is considered as m. This is x and this is and dy. So you can say dou ty dou b. Alright, dou ty dou b keeping s constant is equal to dou py dou s, right? Dou py dou s keeping volume constant. So one equation you can derive from here. Similarly, second equation you can write from here, right? You can say dou ty dou p keeping entropy constant is equal to dou by dou s keeping pressure constant, right? The same fundamental concept you have to use. So since u, h, f and g are the thermodynamic properties and exact differential, so we can use the same analogy like dz is equal to m dx and dy. Then this concept, right? So dou m by dou y keeping x constant is equal to dou n by dou x keeping y constant. So this analogy you have to use, and if you apply this analogy to these four equations, you can derive four Maxwell's equations out of it, right? So as I said that any variables, right, is going to satisfy this condition will be called as exact differential, and any exact differential variable will be known as property of system. So if you apply this concept, right, this concept over this equation, just you compare this equation with this equation first. So m is basically t and it is dx, x is s and y is v and n is p. So you have to differentiate m and n. So m with respect to y and n with respect to x. So here you compare t with respect to v and p with respect to s, and keeping those variables constant. So first equation, if you write first Maxwell equation out of it, you can say dou ty dou v keeping s constant. So you can say dou ty dou v yes is equal to dou p by dou s and v here, right? So first equation can be, you look at here, this is the first equation, dou ty dou v s is equal to minus dou p dou s v. This is the first equation that you got, right? That you got, and minus term was already there. And second equation, if you want to write from here, you can write dou t by dou p s, right? So you can say dou t by dou v here s is equal to here plus, right? So dou v by dou s and p. So dou v by dou s p. So second equation, you look at this, dou t by dou p s is equal to dou v by dou s p. This is the second equation that you got from second equation from here. Now look at this here, both side minus, so you can write plus here. So dou p by dou t bracket v is equal to dou s by dou v and t. So look at here, dou p by dou t v is equal to dou s by dou v t. And if you look at the last equation, here can be written as dou v by dou t p is equal to dou s by dou p t, right, and minus term. So this is here, dou v by dou t at p is equal to minus dou s by dou p at t. So you have written four equation, a partial differential equation. These four equations are known as Maxwell's equations. So these four equations are basically relating all the eight different properties of system, and these are very important relationship, right, in the thermodynamic relation. So like that you can derive four Maxwell equation. Let's go for the next topic, that is called TdS equation. So there are two TdS relation, right? One is for closed system, one is for open system. Let's start with one, right, first. So since entropy may be expressed as a function of any two independent properties, so entropy basically depend on temperature and the volume, right? So entropy is a function of temperature and volume, and we are writing, whenever you are talking about volume as variable, that means what you are talking about closed system case. So we can say ds equal to differential can be written as dou s by dou t v dt plus dou s by dou v t dv. This is the one equation that you have written. Now tds you multiply throughout by t, right? In this equation you can write in this way, right? You have written this. But for reversal process, we know that dq is equal to cv dt is nothing but tds basically. So for reversal process, exactly dq is equal to t into ds. So you look at here, this is cv dt volume constant is equal to ts volume constant. So we can write from here cv is equal to t into dou s by dou t. volume constant, right? So in place of Cv, right, no, in place of this complete term, you can write Cv. So just look at here. Here, this term is available here, dou sy dou t v, right, into t. This is Cv dt, right? So I can say TdS equal to Cv dt plus this additional term, right? This additional term. Now I have to use for this term I have to use the Maxwell relation, right? Maxwell relation. But so from Maxwell relation, right, dou sy dou v at t is equal to dou py dou t at v. This I know from one of the Maxwell equation. So finally I can write TdS is equal to Cb dt plus t dou py dou t at v dv. This is the first TdS relation, right, applied for a closed system, right. Next TdS relation, this is first TdS relation, just you note down. Now next one, for open system, when we are talking about open system, in open system there will be a flow. So in order to have a flow, there should be a change in pressure, right, and temperature is also there. So entropy is a function of temperature and pressure. So using the same analogy, we can write the differential form of it, right, and then multiply by t. We can write TdS equal to t dou sy dou tp dt plus t dou sy dou p at t and dt dp. So now we use the analogy of heat transfer in an open system, right? So heat transfer in open system is change in enthalpy basically. So dh cp dt, right? So that's concept we have to use. So using the same concept, right, cp dt is equal to tds, right? You can write cp is equal to t dou sy dou t into p. So this complete term is known as cp. So this term is here, right? So this term is known as cp, and this for this I can relate this s and p in respect to pressure and volume using the Maxwell's equation, right? One of the Maxwell equations. So from Maxwell equation, dou s by dou p at t is equal to dou v by dou t at p minus. So in place of this, I can write this minus. So if you substitute the value, I can write TdS is equal to Cp dt minus t, and this term is getting replaced by this term minus dou v by dou t at p. This is known as the second TdS equation applicable for the open system or flow processes. So like that we are having two TdS relations. Now we'll see the difference in heat capacity. We want to derive Cp minus Cv. So you look at in first TdS we are getting Cp and means first TdS we got Cv and second TdS we got Cp. So we have to basically subtract the first equation from the second, right, to get the Cp minus Cv, right? That's what we are going to do. So difference in heat capacity. So if you look at the TdS equation, these are the two TdS relations that recently we have derived. This is for open system, this is for closed system. So now you take this term this side, so Cp minus Cv dt is equal to take this term that side, right? If you do the rearrangement of the terms, you can write this equation Cp minus Cv dt is equal to temperature dou v by dou Tp dp plus temperature dou p by dou Tv dv, right? Now take dt out of it. So dt is equal to, you divide this equation completely by Cp minus Cv. I can write in this way. In this way, since temperature is a function of pressure and volume, because temperature depends on pressure and volume, so dt can be written as dou t by dou p v dp plus dou t by dou v p dv. So this complete dt that you are writing here can be replaced by this complete equation, right? So if you substitute this term here, right, in place of dt you write this, and then you rearrange the terms, right? So comparing, just you compare these two equations, because this is also dt, this is also dt. So this first term can be said equal to this, right? So this and this can also be compared with this equation. So comparing 1 and 2, you can write these two equations, right? So first equation is this is exactly equal to this term, right? And this complete term is equal to dou t by dou v at p. I got these two equations, right, by comparing first and two. So both of these, right, both of these, either you can use Cp minus Cv is equal to, you multiply this, or you can take Cp minus Cv if you multiply this. These both will give the same form of equation at the end. Cp minus Cv is equal to temperature dou v by t pressure and dou p by t volume. So I got this Cp minus Cv, and that's what is the required expression. Now we have to express this volume, temperature and pressure and temperature into very simplistic form. Already we know this fundamental equation, right? This is the first derivation that we have derived. How pressure, volume, and temperature are related by equation, that is nothing but dou p by dou v, dou p by dou t at volume, and dou t by dou v at pressure, and dou v by dou p at temperature is equal to -1. Just look at this term right here, which term basically is matching with this, right? Only this term is matching, and this equation, this term value we can take from this complete equation. So this term is available here, that is nothing but -1 divided by this term, or you can just reverse the things, the dou v by dou t at p. So from this equation I can say dou p by dou t at v is equal to minus dou v by dou t at p multiplied by dou p by dou v at t. So substitute this value right in this equation, so if you substitute this complete thing here, you can write Cp minus Cv is equal to minus T, and this dou v by dou t, dou v by dt will multiply, will become square into dou p by dou v at t. So this is the final equation. Now you just look at this equation. So following observations can be done, right? This pressure will always be, change in pressure will be negative, because whenever there is a flow, right, this term will be means a pressure term will be negative. So negative and negative will be positive. So we can say Cp minus Cb is always greater than 0, or you can say Cp is greater than Cb. One outcome can be given. Second outcome, if you are comparing just the liquid, that is water. If you talk about the water volume, specific volume will be negligible at 4 degree, where density is maximum. That is going to be the case. Then Cp will be exactly equal to Cv. So in the case of liquid, there is no difference between Cp and Cv. Second important observation can be made. So first observation is this term, complete term, will always be positive, and this is negative, right? So that means Cp minus Cb is always positive. Second, when temperature is going to be 0, right, in that case Cp will be equal to Cb. Cp always means Cp will be equal to Cb, right? A third case, when this term is becoming 0, right, that means at 4 degree, in the case of water, right, especially volume is minimum. So for water particularly, Cp will be equal to Cv. So these are the three important observations made out of this equation. Now we have to express these terms, right, in terms of very fundamental equation that we know, Cp minus Cv is equal to R. So we have to express this in terms of R. So we have to use the fundamental relations, right? Ideal gas equation of state. So let's suppose we are considering a perfect gas. For that PV is equal to MRT, then we can find out this partial derivative values, and we substitute the values here. Then we see whether it is exactly giving the same value that we are using already, Cp minus Cb is equal to R. So if you do so for ideal gas, PV is equal to MRT, we can say dou V by dou T, keeping pressure constant. Just differentiate this by keeping pressure constant. I will get only Mr divided by P. So Mr divided by P is nothing but, this is nothing but V divided by T, right? Look at Mr is here, divided by P is nothing but V divided by T, right? So I can substitute V divided by T. So dou V by dou T is nothing but V divided by T, and similarly dou P by dou V, because I need two terms, right? Dou P by dou V, keeping temperature constant, differentiation of volume with respect to temperature, keeping pressure constant. So now dou P by dou V, keeping temperature constant, just look at this equation. I am differentiating dou P with respect to dou V. So this is becoming divided by V. So minus 1 by V square will come here, right? If I differentiate. So dou P by dou V T is equal to minus MRT divided by V square. So I got this value, I got this value. If I substitute these two values right here in fundamental equation, here and here, right, dou V by dou T is simply I got V by T whole square, right, and this dou P by dou V I got MRT by V square. If you substitute these two values right in this fundamental equation, if you solve it, you will get Cp minus Cv equal to M into R. That is the required thing, right? This is the total capacity, right? Cp and Cv. If you write in a specific heat capacity, Cp minus Cv, that is just R, where R is characteristic gas constant. So this is the fundamental equation that we were using, and we have already proved it via the thermodynamic relations. Now let's define two more coefficient. So we are going to define the volume expansivity, that is known as beta, and isothermal compressibility. So if you look at the volume expansivity, that is not that is isothermal. Basically condition is isothermal expansivity and isothermal compressibility. So volume expansivity, if you say this is isobaric, so we can say dou v by dou v, this is the volumetric strain divided by temperature keeping pressure constant. And isothermal, when temperature is constant, two variables will be changing, pressure and volume. So this is similar like your bulk modulus. So kT is equal to minus dou v by dou v divided by dou p keeping temperature constant, right? So this first term is known as volume expansivity, second term is called isothermal compressibility. So now basic idea is we are going to express the Cp minus Cv in terms of beta and kT. So so what you need to do, you just divide and multiply by v square, right? Volume square. If you multiply here by v square and divide by v square, take that v inside here, 1 by b whole square. So only b square is pending. Then one more modification you do, divide that b square into two form, b into v, right? Take one b here, take another b as 1 by b with this, right, with this term. So look at here, the same term I have done, I have multiplied divided by b square. So 1 by b square I have taken here, and multiply of b square I have divided in two parts, one b I kept here, another b I have taken here, 1 by v. So look at this term and look at this term, this is nothing but exactly these terms which I am getting. So if you substitute the value of beta and kt, I can express Cp minus Cv in terms of beta and kt in this way. So Cp minus Cv is equal to Tv beta square divided by kt, right? So like that you can express Cp and Cv, right, in terms of volume expansivity, right, and what we say isothermal compressibility, right? This is also very important relationship. Next, go for coefficient of expansion and compressibility. Let me define what are those. Already I have given you the overview of that. All right. So if we draw the pressure versus volume, right, where no temperature and volume, that means the pressure is the constant parameter. So on volume and temperature curve, right, if you are drawing this line, these are known as constant pressure line, or we can say isobaric line. So slope of isobaric line is nothing but dou v by dou t at a pressure constant. This is the slope. So if you reverse the ordinate, right, in place of temperature here and volume here, if you ordinate getting changed, this isobaric line will be behaving like this, right? And slope of this is dou v by dou t, similar like here also at pressure constant. So if we divide this gradient, this slope by the volume, right, basically we can get the what we say, the coefficient of expansion, that is 1 by v dou v by dou t keeping pressure constant, that is known as coefficient of cubical expansion, right? The value of beta can be tabulated for a range of pressures, right? Different pressures will have different value of slopes, right? So this value of beta can be tabulated for a range of pressure and temperature, and can be plotted, right, in a similar way. We can draw it. Experimental data, we get beta and we can replace that by the isobaric lines, right? For solid and liquids over the normal working range of pressure and temperature, the expansion is very small and can be neglected. Only in the case of gas, the expansion will be more, right? Expansion will be more. So this is known as the coefficient of expansion. Next one is coefficient of compression. So volume and pressure curve, if we draw this line, this is known as isothermal lines, right? Slope of isothermal, if you draw like it is come as dou v by dou p at t. So look at the slope always will be negative, right, in this case, right? And if you change the ordinate, right, if volume is coming here and temperature is coming here, in that case we draw, this is called isobaric line. This is like earlier case. So here slope is negative, that's why we are writing k is equal to minus 1 by v dou v by dou p t. When you divide this gradient by volume, you will get the coefficient of compressibility, coefficient of isothermal compressibility, you can say. So k is equal to minus term is coming because slope is negative. So the volume of substance always decreases with the increase of pressure when temperature is constant, right? So we can say k is equal to minus b2 minus b1 divided by b1 p2 minus b1. This term is known as coefficient of compressibility. So these two terms are very important, right, with regard to finding out the difference between the gas and liquid. So whenever I talk about bulk modulus is basically defined for liquid. and as well as it is applicable to the gas. In gas case, right, compressibility is high, very high compared to the liquid. The liquid are less compressible compared to the gases. Gases are highly compressible. So these are the two coefficient, right, coefficient of expansivity, right. So dou p by dou v by dou v by dou t at pressure constant, and this is the coefficient of compressibility, where this is minus 1 by v dou v by dou p, t by dou v by dou p is nothing but slope of isotherm, and slope of isotherm is negative here, right, but slope of here, slope it was positive, here it is in this case slope is negative, right. That's the basic difference. So compression means volume is decreasing. Another way you can physically you can say volume is getting decreased in compression, that's why its negative term is coming, right. And expansion, when you talk about expansion, volume is getting expanded, that's why positive term is here. So positive dou v by v dou t by dou t, keeping pressure constant. These two are the important variables, right. K can be regarded as constant for many purposes of solid and liquid. So with this I am closing the today's discussion, right. So today agenda was basically to give you an idea about thermodynamic relationship. We have derived expressions for the general relationship between pressure, volume and temperature, that is equal to -1. Then we derived two expression, TdS relation, one is for closed system and open system. We have also derived expression for difference and specific heat capacity, Cp minus Cv, in terms of the fundamental equation Cp minus Cv is equal to Mr, and also we have expressed the same Cp minus Cv in terms of the coefficient of expansivity and coefficient of isothermal compression, right. So this much is enough for today, right. Next class when we will meet, we will derive expression for the change in entropy, change in internal energy. Then we will go for finding out the change in enthalpy in terms of partial derivative of the properties. Alright, so if you are having any doubt in this, right, feel free to write in the comment section, or you can directly approach to me. Already I shared with you my WhatsApp number. So see you all right in the next class. Have a nice day. Good day.